Welcome to the Noisy Channel. We make fun, accessible explanations about topics in the intersection of math, computer science, and electrical engineering. Most of the time, our videos are specifically about information theory, a field which borrows many aspects of each. For math, it draws heavily on probability, analysis, and combinatorics. In computer science, it relates to machine learning, complexity theory, and computability. In electrical engineering, it connects to communication, coding, and signal processing. We thought it'd be a good idea to explain why we chose our name, because we certainly hope our videos are more than just noise to you. Information theory began as a mathematical formulation of communication systems, which are things like Wi-Fi, 4G, phone lines, Bluetooth, and even regular human speech. For human speech in particular, information theory would model two people talking by saying the person in red on the left is the information source, the person in blue is the receiver, and the space between them is the channel. We have all had the experience of trying to communicate in a noisy situation. Maybe you're at a loud party, or maybe there's an extremely vocal cat also in the room. Information theory usually includes noise in the channel model, because in real life, there are many things that could cause a signal to not be transmitted perfectly. Anything from a broken wire to moving too far from a Bluetooth speaker. Whenever engineers and researchers are going to discuss a problem or build a new system, they need a clear, shared language. They turn to math. Let's introduce some mathematical notation. Call the source message X and the noise Z. We are saying that when transmitting the message, there's a chance the noise might interfere in some way. Therefore, the channel is a function f that takes in X and Z and produces some output. Depending on the situation, noise may affect the message in a big way, like a cat meow might be so loud entire words get misheard, or the noise could be very small. The function can be anything, so this way of modeling a communication channel is very flexible. In this noisy room model, what the receiver hears on the other side is entirely determined by f of x and z. We often call this output x hat, to show that what the receiver understood from the message is related to x but might not be equal to what the source was saying because of random noise. This ingenious idea of abstracting a source, channel, and noise with symbols is the foundation for every part of digital technology. It allows us to describe all sorts of signals and ways of transmitting and receiving them without having to use separate models for each use case. All of this came from Claude Shannon, an American researcher, who became interested in a mathematical theory of communication in the 1940s. By formulating the channel model, Shannon created the entire field of information theory. This area of research took off and led to faster and more reliable communication networks. The tools that information theorists have developed are so powerful, they have also been used to solve hard problems in all sorts of surprising places. For example, entropy helped advance our physical understanding of the universe by demystifying Maxwell's demon paradox. It is no longer a paradox if one takes into consideration the information the demon would need to store. In 2015, mathematician Terry Tao solved the Erdős discrepancy conjecture, which had been open for 80 years, and explained his solution using entropy of random integers. In economics, our understanding of gambling is enhanced by using information theoretic tools. Finally, machine learning has benefited from information theoretic results about the difficulties of learning classifiers from noisy data. Now we hope you'll understand why we love noisy channels so much. We hope you'll stick around and subscribe.